Section 5.2, some particular forces. So in this section, we'll take a look at some of the forces that can go into Newton's first and second law, into the net force. What forces do we have out there? Well, let's take a look. So first we have our gravitational force, which we note with an F sub g. This is a pull that acts on one body directed toward a second body. So generally we're going to consider situations where the second body is Earth, gravitational force due to Earth. So we might have consider, okay, what pull does the ball feel to the Earth, the secondary object? So in free fall, if you're in the y direction with no drag or air resistance from the air, then you could say, hey, the net force is the force of gravity pulling you down. So it's negative force of gravity, negative showing the direction, is equal to the mass times the acceleration, which in free fall, the acceleration is just negative g, as we've seen before. So in other words, this gives us the equation that the gravitational acceleration or gravitational force can be calculated with the gravitational acceleration g, right? In other words, gravitational force is mass times g, that 9.8 meters per second squared. Now, we derived this in the free fall case, which is what we've previously been considering in projectile motion, chapters 2 and 4. But this force will still act on a body that's at rest. So even when the tennis ball is supported by my hand, it still feels the force of gravity that is pulling it down, which is part of why it stays anchored in my hand and doesn't just float away. We can write this as a vector if we note that the FG vector is negative j hat direction. Or you could plug in mg and say that that's negative mg j hat. You could even, sometimes people use the notation of mg vector, where the vector implies the negative j hat direction. That seems a little bit loose to me. I like the negative mg j hat better because g is always a positive 9.8 meters per second squared. So to me, that keeps it clear that the direction is negative j hat, while g is a positive constant. Now, closely related to the gravitational force is our concept of weight. Weight is just the name given to the gravitational force that one body, like the Earth, exerts on an object. So in practice, we use gravitational force and weight fairly synonymously. Weight is an example of the gravitational force. The gravitational force is the general, more broader category. So weight is a force measured in newtons, directed downward towards the center. So we all feel pulled down from the Earth, and it's really towards the center of the Earth. So weight, assuming that ground is an inertial frame, is equal to the gravitational force. And so because the weight of a body is equal to the magnitude of the gravitational force on the body, we are typically going to work with the gravitational force. That's what the book does. It just describes the downward pull due to this gravitational attraction to the Earth and not the weight. And that will make it clearer because W, we will later see, also stands for work. So F sub G is our way of describing the downward pull that we all feel, which can be described as weight. Now, if we want to measure weight, it's not the same as mass, right? Note weight is a force. So it would be different first if we're on Earth versus we are on the moon. We would have two different weights even though our mass is the same. So if you want a quick weight loss scheme, just fly to the moon and you'll weigh less. You might be just as massive, but you will weigh less. So, hey. Another detail that perhaps is a little bit closer to home is that the weight must be measured when the body is not accelerating vertically. So you can get your weight if you are in your bathroom and you step on the scale, or even on a train. The train can be accelerating horizontally, and you still be able to weigh yourself. But in an elevator, if you try to weigh yourself on a bathroom scale, you'll get different values depending on the motion of the elevator. You'll see that you get a larger value when the elevator first starts to go, when it accelerates upward. You kind of feel it, you kind of feel heavier. Once the elevator gets going steadily and there's no acceleration, constant velocity, then you won't feel anything. It'll be the same as normal gravity. And then the elevator starts to slow down near the top, and you kind of feel lighter, right? Because of the negative acceleration. Pretty wild stuff. So the weight needs to be measured when you don't have that vertical acceleration. All right, another force we have is the normal force. This is a pretty typical force, you might say, but in this case, we aren't referring to normal as in typical or everyday, though it does occur every day. This is the mathematical definition of normal, which is perpendicular, right? So normal means perpendicular. And this comes from, if you're standing on a surface, this is the push back on you from that surface. And it's from deformation. So if I push against the wall pushes back on me, right? Or the tennis ball, which is being pulled down by gravity. So it's pushing into my hand, and my hand is supplying a normal force upward in order to support it so that it doesn't fall towards the center of the earth. So when a body presses against a surface, the surface, even a seemingly rigid one, deforms and pushes on the body with a normal force F sub n that is perpendicular to the surface. Right, so we can look at this drawing of the block on a table. This is a pretty nice example here. And there's the normal force that is pushing up on the block, and that's from the table, and it's in response to the block pushing down on the table. So here the forces are shown, drawn closer to where they're acting on the block. If we wanted to make a free body diagram, we'd shift over here where the block becomes a single dot, and the normal force is going up with the tail connected to the dot, and the force of gravity or the weight is going down. And so we could mathematically look at this. If we go back to Newton's second law, which is going to pop up quite a bit, we know that F net is equal to mass times acceleration. And here we're going to focus on the y direction. Why is that? Well, because we only have forces in the y direction. So we have, what forces do we have in the y direction? Well, we have this normal force, F sub n, and F sub g. So I'll fill those in, F sub n and F sub g. And what we're going to have to fill in when we're doing the net force is the direction that these forces are acting. So the normal force is in the positive y direction, so I'm going to add a plus. The force of gravity is in the negative direction, so I'm going to add a minus there. And this is equal to the mass of the block times whatever acceleration there is in the y direction. So if the acceleration is 0, then we'd see that the normal force is exactly equal to the weight of the block. One other note that's really easy to confuse with the normal force is notice F sub n for the normal force looks very similar to our F net, but they are not the same. So the normal force is not equal to the net force. That's something you want to keep straight. And if it's at all confusing for you, I encourage you to write it out as F subnormal, something like that. All right, so looking at an example here. Normal force for a block resting on a horizontal surface that is accelerating vertically at a sub y or vertically at rest. We've already done the work for that because we used that free body diagram with Newton's second law. To get an equation for the normal force, all we have to do is add the force of gravity to the other side, and we'll have our equations. So the normal force, if we are accelerating vertically, is equal to the weight, mg, plus mass times that vertical acceleration, a sub y. We can even factor the mass out. And then we see that it's equal to g plus whatever that acceleration is. If it's vertically at rest, or even vertically moving at a constant speed, then we'd see that a sub y is 0, and so the normal force is just equal to the weight. Right, so now that we've seen this example, let's take a look at a checkpoint. So it says, in the figure, is the magnitude of the normal force greater than, less than, or equal to mg if the block and the table are in an elevator moving upward at A, constant speed, B, increasing speed. So I want you to think this through, come up with an answer to parts A and B before you move on. Go ahead and pause now. Right, did you pause? Hoping so. So the key here is paying attention to the acceleration. We can use what we have on the previous slide of the equations for the normal force. So in part A, it says constant speed. If the speed is constant while it is moving upward, then what is the acceleration? Part A, the acceleration is 0. If the acceleration is 0, that tells us that the normal force has to be equal to mg for that to work out. Now, what about in part B? Part B, we have increasing speed. If it's increasing speed while it is moving upward, that tells us our acceleration is no longer still 0. But we have to determine, is our acceleration positive or negative? So is it greater than 0 or is it less than 0? Right? Well, that's where we think, okay, if it's moving upward and its speed is increasing, then the only way we can have the speed increase is if the acceleration is in the same direction as the velocity. So if the velocity is up and the speed is increasing, then the acceleration will also need to be up. Or in other words, the acceleration must be positive. If we have a positive acceleration, that's going to add to the weight. And so the normal force is going to be greater than the weight, because we also have to, the normal force is also supporting this additional acceleration upward. It's a way that we can think about that. So it is indeed C and then A, following this equation as described before. Right, now another force that we have is the frictional force, which is usually referred to as just friction. This occurs when one object slides or attempts to slide across another. So it's directed along the surface opposite the direction of intended motion. So if the block is attempting to slide to the right, the force of friction is acting to the left. And we note that it is a lowercase f. That's a little hard to see there. We use a lowercase f to denote friction. This is something we are going to explore in chapter 6. So we just mentioned now that it exists, but for chapter 5, everything will be frictionless. So smooth sailing for this chapter and more to come with friction. So stay tuned to get to find out more about how friction works. Right, then we also have the tension force. It could be a cord, like a rope or a string, is attached to a body and pulled taut. Cord pulls on the body with a force T that is directed along the cord. The cord is said to be under tension, and the tension in the cord is T. So a massless and unstretchable cord exists as only as a connection between the two bodies. So it's going to pull on both with the same tension force T. So if you have, say, some sort of cord, right here using my keys, then if I'm pulling on one side with a force of 5 newtons, the other side will feel that same force of, say, 5 newtons. It's the whole cord is under that tension that is the same throughout. So this is true even if the bodies in the cord are accelerating, and even if the cord runs around a massless, frictionless pulley that changes its direction. So these are some useful simplifying assumptions. In practice, a cord is going to have a small amount of mass and be slightly stretchable, but it often is much, much smaller, so that it's insignificant compared to the mass of the objects in question. So some visuals that show this: if we have a block and we're pulling on it, right, the cord is pulling on the block with a tension T, and that's pulling back on our hand with that same tension T. That's equal to our pulling force. Similarly, if you add a massless, frictionless pulley, then we can write the same tension pulling the block sideways as pulling upward on our hand. So even two different objects, as long as we have the same cord connecting them, the tension has to be the same. Finally, it's even true in this case where both the tensions are going up, right? It's pulling the block up and it's pulling up on the hand, and yet they have the equal magnitude. Even though the directions in all 3 cases are different, the magnitude of the tension stays the same. All right, now let's look at one more checkpoint. It says the suspended body in the figure weighs 75 newtons. Is T equal to, greater than, or less than 75 newtons when the body is moving upward at constant speed, at increasing speed, and at decreasing speed? So I want you to think this through. You can use some math perhaps to help you, or use a more qualitative approach. There's a number of ways to think about this. So please go ahead and pause and come up with an answer before you move on. Right, did you come up with an answer for all 3 parts? I'm hoping so. Well, if we know the suspended body weighs 75 newtons, we can go back to our Newton's second law, right? Once we figured out our forces. So we have the tension force going up, and then the force of gravity pulling down on it with the 75 newtons, right? And so then we can say, hey, the sum of the forces in the y direction, which really we should probably draw a free body diagram first before plugging into this. Sum of the force in the y direction is equal to mass times acceleration in the y direction. So our free body diagram, we make a dot for the block, tension goes up, and the force of gravity goes down, which is our weight of 75 newtons. There we go. And we could add a vertical axis here. Not too stressful or critical, but cool. So that's looking good. So our forces then, we have tension minus 75 newtons is equal to the mass times the acceleration in the y direction. So if we're moving at constant speed, acceleration in the y direction will be 0, tension will be exactly equal to this 75 newtons, right? And then we could say if we're moving at increasing speed while moving upward, that's going to be a positive acceleration. So that's going to add to our overall tension. Our tension is 75 plus a positive mass times acceleration. Versus when we are going down, then the acceleration becomes negative, or sorry, when we're going up at decreasing speed. If we're still moving up with our velocity, but to decrease the speed, the acceleration must be in the opposite direction, negative. And so that will produce a tension that is less than 75 newtons, matching our experience in the elevator. And you can even think about it as if we need to accelerate this block, then we need to have a larger tension force than the 75 newtons in order for it to like get it moving faster upward, right? Versus when we're slowing down, we're kind of like putting the brakes on so we can reduce the tension force and let the 75 newtons be larger to have the downward acceleration. So I like that visual way to sort of depict the different magnitudes of the values. So what we find is that it is equal when it's a constant speed, greater if we have a positive acceleration, and less than 75 if we have a negative acceleration, which is reducing it. So we've now introduced all of our particular forces, so we'll get to apply them in the next section. Stay tuned.